Welcome to Study Loop.
Hello everyone, today we're doing chapter 17, problem 62. In this problem, we're given the structure, this molecule here, and we're asked 4 questions. A, explain why the nitrogen heterocycle, so this cyclical structure here, is aromatic. B asks, what type of orbitals is the lone pairs of each nitrogen atom existing in? C asks us to draw all resonance structures for this molecule, and D asks us to explain why the pKa of the nitrogen-hydrogen bond, this bond, has a similar pKa for an OH bond, so an alcohol group, making it considerably more acidic than amines such as this, with a pKa around 40. So let's first tackle part A. So part A, why are the nitrogens in the heterocycle aromatic? So why is this heterocycle aromatic? Well, let's look at the structure. So we know that nitrogen has lone pair electrons on each atom. We know that to determine aromaticity, you must follow Huckel's 4n+2 rule. Be cyclical. Every carbon must be sp2 hybridized, and it must be planar. What else we know is that lone pair electrons can also be considered pi electrons if they satisfy some few criteria. One of those being that it must not exist on a heteroatom that it has double bonds. So this nitro atom that has double bonds, we know that these 2 electrons are not going to be in the p orbital that are delocalized around the ring. They are in the p orbital that are in the plane of the carbon-carbon bonds, therefore not involved in aromaticity. What about this nitrogen? Well, this nitrogen has already its 3 bonds on the plane of the carbon-carbon ring. So that means that these 2 lone pair, or this lone pair electron, is now in the p orbital that is going up and down. So this nitrogen's electrons are able to delocalize around the ring. So they will be contributed in the determination of aromaticity. So in total, we have 4 electrons from those 2 pi bonds, and we have 2 electrons from nitrogen. So we know that we have 6 pi electrons, 2 from the lone pair, 4 from the alkene bonds. And the specific, these 2 from the lone pair, is from the nitrogen that does not have a double bond attached to it. So we know that it follows the Huckel's 4n+2 rule with n equaling to 1. So yes, this molecule is aromatic. So what about in B? B asks, in what type of orbital is the lone pair of each nitrogen atom contained in? Well, we kind of already answered this in the termination of A. We know that this, because it's able to delocalize, this must be, these 2 electrons, lone pair electrons, must be contained in the p orbital because they're being able to delocalize and they're pi electrons. These electrons, we kind of already answered that they're not in the p orbital because they're not able to delocalize around the ring. So therefore, they must be in the sp hybridized orbital. And how many sp? Well, remember, we have s to the power 1, but nitrogen is bound to 1, 2, 3 things. So one of those things is a lone pair, one of the things is a double bond, one of the things is a single bond to nitrogen. So this nitrogen is bound to 3 things. So we have s to the power 1, so we need 2 more things. So we add p2. So 1 plus 2 equals those 3 things. So we have an sp2 hybridized nitrogen here, and we have a p orbital over there for the bottom nitrogen. In C, draw all resonance structures of this molecule. So I'm going to draw these 2 rings only, this 5-member ring and this cyclohexane ring, because the other portion of the molecule is not included. So I'm going to draw up till here. So let me redraw the molecule to begin with. Let me draw that better. So we have nitrogen. Whoops. Nitrogen, hydrogen, double bond, double bond. And we have this cyclohexane ring. So what we know right off the bat is that these electrons of this nitrogen are in the p orbital, so they'll be able to delocalize around the ring. So let's start by delocalizing these electrons around the ring. So let's make a new bond between the 2 nitrogens, making a bond. When you make a bond, you need to break a bond, so then these 2 electrons on this pi bond are going to go onto this carbon nucleus to form a carbanion. So now this nitrogen has now 4 bonds, giving it a formal positive charge, and this carbon has now extra pair of electrons, so it's going to be negatively charged. And we still have that double bond here, and we still have our cyclohexane ring. Well, next what can happen? Well, nitrogen does not like having extra electrons and like being negatively charged, so it's going to make a new pi bond over here, moving these 2 electrons of this pi bond now to this carbon atom here. Remember, your resonance structures are illustrated by double-headed arrows. This nitrogen still has a positive charge. But now we have a pi bond here, pi bond there, and now we have a carbanion at this carbon here. So next what can happen is carbon once again does not like having extra electrons, it likes being neutral, not negatively charged, so we can move these 2 electrons to make a new pi bond with this nitrogen, making a bond. When you make a bond, you break a bond, so then these 2 electrons will go to form a new bond here, making a bond. When you make a bond, you break a bond. Now these 2 electrons will go onto this carbon nucleus here. So now you see kind of why I only need this cyclohexane structure, not this entire molecule, because there's actually no conjugation involved in this molecule. So we already know that only the portion where the double bonds are going to be involved for resonance structure, not the portions with just straight chain alkane. So we now have a new double bond here. So nitrogen still has 4 bonds, still positively charged. But we lost that double bond between nitrogen and nitrogen, and now we have the carbanion over here. So now what can happen? Let's see. So now what we can do is kind of move it backwards. So we can take these 2 electrons, move it back to make a new pi bond here, making a bond. You make a bond, you'll break a bond. So now nitrogen will pick up these 2 electrons on itself. So now it's going to get 2 lone pair of electrons itself. So this nitrogen still has a positive charge. And notice that the overall charge of the molecule does not change. We have a positive charge here, minus charge here, so still neutral here, still neutral here, and it's going to still be neutral here. So let's draw this structure. So what do? We added a double bond here. Now this nitrogen picked up an extra lone pair of electrons, giving it a negative charge. So now we have this resonance structure here. So now what else can happen? Well, now from having this pi bond, and this carbon only has 3 things bound to it, we can break this pi bond and go over here, making a bond. We make a bond, we break a bond, so we'll finally move this pi bond onto the nitrogen nuclei, neutralizing it. But in the process of that, we're actually going to form a carbocation. So now we have a carbocation here because we just lost that 4th bond. So we only have a carbon with 3 bonds now. And now this nitrogen is actually going to be neutralized because it has only 3 bonds. And this nitrogen is still negative because it has that extra lone pair electrons. So the final resonance structure we can draw is we can move around this carbocation intermediate. So we can move this carbocation over to this carbon here by moving that pi bond. So now we have a carbocation at this carbon here. So in total, we have 2, 4, 6, 7 resonance structures possible for this molecule. So now we can move on to part D. Well, let's see what part D asks us. Well, part D asks us to explain why the pKa of this nitrogen-hydrogen bond, so this bond right here, this nitrogen-hydrogen bond, why is this pKa similar to that of an alcohol pKa bond? This makes this quite considerably more acidic than a bond on this amine group, this ethylamine group, with a pKa of 40. Well, let's look at the hybridization of this. So we have a nitrogen with 3 things attached to it, so this is going to be sp2 hybridized. But this thing here, because the lone pair electron is now on the p orbital that is in the plane of carbon-carbon bonds, it is not actually able to delocalize around the ring. Because of that, this is actually going to be an sp3 hybridized orbital. So because of that, in total, this nitrogen-hydrogen bond has a total characteristic of 33% S characteristic, while this has 25% S characteristic. So we know that increasing the S characteristics will increase the acidity of your heteroatom hydrogen bond. So because of that, we have an sp2 hybridized atom with 33% S characteristics. We know that this nitrogen-hydrogen bond is much more acidic than this nitrogen-hydrogen bond that has only 25% S characteristic. So this actually has to also due to the stability of the conjugate base. So when we actually lose this hydrogen, we gain 2 electrons. So by gaining 2 electrons, we can actually delocalize that around the ring. However, here, if we lose this hydrogen, these 2 electrons are localized only on this nitrogen nucleus and not around the entire ring.